Morning. All four of you. I was in China in May. Supposed to go back to China here shortly, and I was in Jingdezhen, which is the birthplace of porcelain, and I toured a tile factory. Since we're talking about pressing, my intention is to show you images because they're very interesting. But it turns out that I can only send so many at a time. So that's sort of a problem here. I got to figure out which ones got sent. But they don't seem to pay attention to the weekend. Toured 6 factories on a Saturday, and which is a lot, no matter how you look at it. But anyway, one of the factories is a tile plant, huge tile facility making porcelain. And figuring out which files I decided to send me is hard. The files are just too big to send either. Try this again. Do the same thing. But there's a really interesting thing that happens, and it's fascinating because we've been taught something that isn't true. I didn't understand that until very recently. So, of course, it keeps a lot of things that are true, but this one in particular has importance. So, when this all gets figured out here, it has to do with large format tile production. And how you manage to do that. So, let's look at this. Okay, so this is where we are in terms of the class. We're talking about dry pressing today. I'm going to leave the lights off if we can. Issue with this, that, okay, so we do the classical discussion about dry pressing. Right? We do this, log pressure versus density. The curve looks like this, and actually this difference here is very shallow. P2, P1, 1, 2, 3. This is elastic, and this is plastic deformation, which we talked about in class last week, or yesterday, whatever it was, right? This transition, P1, is called the onset of granular deformation. So it's where the granules start to break down. So all this material is spray dried or granulated. And they do that. Do you know why they granulate?
Better.
And actually because it flows better. So everything about dry pressing, we teach you this as academics. This is useful, but arguably kind of worthless, okay? And so when I was a co-op student, I worked for a company that made honing equipment, abrasives. And they had a mixture of fused alumina or silicon carbide with, in the case of silicon carbide, you have a porcelain bond, actually. In the case of fused alumina, you have a glass bond. And so what you do is you mix that raw powder, the glass, you don't typically use a frit, you have a batch that you mix with your granulate, with your abrasive grain, and then that material gets fed by hopper into a die. So there were a lot of questions, and one of the problems they had was uniformity of that brick that they were making. It's like a grinding wheel. And the problem is this, that they need, what they found was that if they had more bond, this porous system, not dense, they have more bond in one region than another, that there's a linear increase in the hardness of that material with the amount of bond. So now the uniformity of that bond distribution is really important. So one of the questions was, what happens in dry pressing? We did a really simple experiment. So they had a hopper that was set up, the top looks like this, had two tubes, okay, and it was actually shaped something like this, okay, and the tubes come out to feed, this is your tube here, to feed a die. So we did a really simple experiment. One thing we did was we layered material in here, different colors, blue versus white, and then we looked to see what happened when it went into the hopper. The other thing we did is we fed it this way, so we did blue on this side and white on this side, so you have blue coming down this one and this one. And then we pressed bricks, so the shoe would come forward, fill the die with a hydraulic press, and then move out of the way, and then it would press the brick. So we're making a brick that's roughly about an inch or inch and a quarter in height, and about 3 inches wide, and about roughly 9 inches long, 8 inches long, something like that. And so we looked at this brick that was pressed, and when we did layers, we just ended up with layers. But the most important one was this one. When we did the two sides, you would get a line here that was almost perfect, and then you would see this between the two, and you would get blue on one side, white on the other. And that, the way that this would work, you had your shoe come over, okay, with your material in it coming in, and then you had your die, and the punch would extract, and this would move back and forth over this several times as this was retracting. And so you actually came up with layers like this in that material. That was 1982. All right? So we do the math. It took me, let's see, 20, 30. It took me 36 years to figure out what was going on. So I feel like I'm making progress. All right? And what's going on? What's going on is there is no movement. When you press something, okay, like this, right? If you press in a die, okay, like this, we teach you about die wall friction, and you get this going on, you get your compact. There's no movement laterally. None. And I mean, like none, like at all. We get die wall friction. If you look at the classic pressing situation like this, they press a cylinder, right? And then they would look and they go, look, we have density gradients. A classic image comes out of Reed's book. You have low density in the center, and you have, and then you end up with. So this is the low density here in the middle, and then you get your highest density on these corners. And the thing is, I had a student 20 years ago, Jim Doran. Jim Doran would be impressed. I remember his name. Jim Doran did this really spectacular piece of work, and he looked at this figure, but he did it in shear. Okay? So what does that mean? It means he went into the high pressure angular shear cell that we talked about for measuring plasticity that doesn't work, right? And he measured this compaction curve in shear. What do you think? So he actually had his granule in there, and then he sheared that material in the shear cell. Under load, then he increased the load. He did a really brilliant job. He counterbalanced the arm so there was no friction in the system. I mean, truly spectacular piece of work, right? He spent hours figuring this out, and he generated this compaction diagram. He's loading this material, and he's measuring then the compaction by measuring the thickness. So if you recall that, Andrew sure I didn't draw this, but it has a bearing in the middle, okay, and then you have your bottom platen, and then your material goes in here, And then you have the top platen that presses down on that, okay? So from the side, it looks like this. And there's a shaft in the middle, and you end up with, when you get done, you end up with a sample that looks like this, right, a ring. So he's loading this, and he's measuring compaction behavior, and his results were really spectacular. They come in like this. And he sees that his onset of granular deformation decreased, and he gets a higher density in the presence of shear. Does that make sense? Okay, so if you press on a material, if you shear it, the density goes up significantly, measurably different, and P2 decreases also, by the way. P2 decreases a lot, okay? So this is a shear compaction, right? And that explains these corners. Because in the die, the material is being sheared at that corner, and so the density goes up. And there's no shear in the middle, so there's no density improvement in the middle. And so, but the argument has always been that you need the die to keep the material from going out. It does not go out. So Andy Wurzak has been working on, at Oak Ridge, has been working on compaction powders, and they do unconstrained compaction. So instead of having the die wall here, they have a platen, okay? They put their powder on, and then they press it, and it doesn't move, okay? And what that allows you to do, actually, is that you don't have to constrain this. So when you start making tile, like this, like it's in this picture, although this one's still constrained, you make tile that's 2 meters by 3 meters, right? I made it too thick. So your thickness is about 2 to 3 centimeters in thickness. On the really, really large tile compaction presses, they do not have an outside die. They simply uniformly load that powder and they press it this way, and there's no lateral movement to speak of. The edges aren't perfect. So then it goes through the kiln, and then they trim the edges after pressing. Yeah, it's, you know, and the problem is that this is my problem, right? Is that I saw evidence of that 37 years ago, and I didn't understand what it meant. And then it's like, yes, of course, you do not need that constraint on the sides. And tile production is huge. So, but the key to dry pressing is not the compaction. The key to dry pressing is uniform die flow. Everything is dictated by that, because what will happen is, if you have a low density region, that material wants to shrink more in that region. And then what happens is that it cracks, right? Or it warps adjacent to that. So everything is about dry flow. This is awesome. This is great. Okay, so let's see if we can expand. This is the press, okay? And these presses are, you know, China is an interesting place. Have you been to China? You probably have to go at some point. Everyone seems to. They would buy a press from Italy, and then 50 presses show up in China. I mean, they're really, really good at duplicating that down to the last detail. And there's no intellectual property to speak of in China. And while we can argue about what that means, globally it's a problem, but it's not necessarily in defense of China. But, sorry, I might make this like entertaining. This is the thing on the side that tells you who made the press. This is not on its own now. The history of China and the culture of China is not one of individuals owning information. I mean, if you go back to ancient China, the way that China was set up, not set up, but the way that it was administered, you know, frankly, 1,000 years ago, and that culture continues because of the number of people and other things, that regional governors would get together periodically, this like historical information about the city, would get together periodically, and then they would share things that they that had been developed in prefecture or in their, in their states or whatever. And so the best example is probably the wheelbarrow. Somebody, innovative person, invented a wheelbarrow, and then the wheelbarrow's all over China. And you may be entertained by the idea of a wheelbarrow, but it's an immense, labor saving device. And their wheelbarrows are different than ours, so they're very interesting. They have a large wheel, two large wheels rather than the small wheel in the front that you fight all the time. Right? The other thing they developed was, the saddle. Not the saddle, but the stirrups on the saddle. It's a rather big deal if you're galloping after somebody trying to shoot them with an arrow. Turns out the stirrups help. So anyway, when stuff gets to China, they don't have a problem with duplicating it. It's not a matter of ownership. It's a matter of the common good. You may think I had to romanticize view of China, but the fact is that that's the way that they see the problem. So this is dye fill. And the trick for dye fill is then that you see the next image. They have small volumes. You cannot fill powder uniformly within a large area. Do you know why? I took my class to the gravel pit a few weeks ago, 314. And when you pour gravel or you pour granulated material into a cone, the coarse particles end up on the outside. So you segregate by size. So if you make a large region, then you try to smooth that out, you segregate your material by size. By doing this, your segregation by size is limited to a very small area. Okay? And now you have then your defect size would start to, or your non-uniformity will be linked to the size of this little volume that you're making. So the consequence of that is that your dye fill becomes remarkably uniform over a very large area. If you look at the way that dry presses are set up, like for dinnerware, okay, we had a horizontal press. I'll show you a picture of it eventually, and they started pressing vertically is much better. So vertically, the dye opens essentially, and I don't really quite know how they do this. They fill that dye, and then they press this way, and so I probably should say that here so the people that are not here today can see. They press this way, and by pressing this way, when they're done, they open it and the plate comes out, right? Whereas if you press this way, you have to reach in and pick up the plate and move it. A lot more work associated with this. That was the press that we were donated. Okay, but this dye fill is great because you get very uniform dye fill, and that is the key to dry pressing. And so in academia, we don't pay any attention to that because how are you going to navigate or measure variations in dye fill on a small volume? You can't do it. We're not equipped to start doing pounds of material. We're really good at the gram level. We're not really good at the pound level. Let's see, I'll do it this way. This is before fill, and this is where it is filled. So you can start to see this. So this above, let's do this. This material, this is a hopper. It's a large cone-shaped hopper. It's basically like this. And you can see the material pouring on the bottom. This is the vibration thing. So it's turn it vibrates that hopper. You can argue that even that is not such a good idea because we found in our work on this type of thing in terms of compaction, that vibration can lead to segregation also. Then you can see a little gears on the side. This thing moves. This stays stationary more or less. This moves, fills that. Okay, I may even have a video. That's a good scale. It's actually a child, though, not a kid. So, let's go to the next one. Two. Right. Let's see what we have here. Good. All right, so this is the press. It's still a child down here in the corner. turns out the day I was there was the 1st of June, and it was National Family Day, which you gotta appreciate the irony. That means everybody takes their child to work with them. They work on a Saturday rather than, hey, let's go to the park. No, I got it. Let's go to the factory. So anyway, this kid was funny. He was the son of, the other thing that happened, right, is used to have, we were able to have one child in China. Now you have two. Everybody has two right away. They're not right now. So this little kid, at the end there's a line that tells you not to go past this point. And I'm in there, and he comes up and he did that all by himself. He comes up and he pulls on my shirt and he puts the line. And you're not supposed to be in there. It's like, this is the press, okay? So, and this, what's coming out here is the just pressed tile, okay? And this is again the fill situation. And so the material is pouring out, but it pours into this rack, and then that rack moves with the bottom sleeve to the, it moves to the bottom, and it takes that material over to where the press is, and pulls out the bottom sleeve. And that material only drops, the distance into the die. It doesn't go very far, but it goes as these little volumes, okay? And then the rest is screeded off, so you don't have any issues with the excess. It gets put someplace else and goes back and gets recycled. And then it moves out of the way, and then the press comes down and presses. And this is just an idea of scale, okay? These are, I don't know, you've got 100 tiles stacked up, whatever they are, shrink wrap. The tunnel kiln is in the background, okay, and you get an idea of the scale. Next image, I think, out of images here, and so I gotta go to the third. I know what you're thinking. You should have planned ahead. These are bigger. Think about that. So, I don't know why. Like that. So, key is uniform. Oh, that's better. Still waiting to download. Well, because Google can't scan my images. So I'm convinced my images go back to China and then come back to me. When I was in China, Google was banned. Remember that ban? Google, you remember reading about that? So then I had anything associated with Google wouldn't work. So my Gmails didn't work. And, I had couldn't get online. All right, so this is good. This is what they're making. So this is not the pressed surface, and it's not a glazed surface. This is a polished surface. So they make a porcelain tile, and then they take that porcelain tile and they polish it, and it's quite a process. So they have large polishers that polish wet. This one actually may be glazed. Yes.
Where's that like color variation?
They do that intentionally.
Okay.
So these are actually not glazed, effects. But what they're trying to do is mimic marble. Mm-hmm. Right? They also have examples in Spain where they mimic wood, but they're getting better. And when I say they're getting better, is that they actually, there's no pattern. In other words, it's not this one. You sort of the thing. You go and you look at a tile wall and look for the repeat. Right? There's no repeat. So they're now the Spaniards developed, call them nano inks, and they developed inks for ceramic inks that are very small particle size, which is interesting in a whole lot of reasons. And then it can inkjet print. And the inkjet print at a remarkably fast rate, but that means that every pattern can be different. So they are somehow able to, from sort of a expert system perspective, they make a pattern and the pattern changes again, so that you lay this all up and it looks like it's wood and it looks like it's all different. But they developed the inks, and then the Chinese borrowed them. Now they make their own. So yeah, there's the tile production. I think these were still warm over there. And then this is how they polish. So these are abrasive packets, and they're set up, and they're spinning, right? They spin, and the tile comes in, and they polish the tile flat, and they actually end up when they're all done. This is where it starts. That's where it ends. And they take them off. And this the 800 here indicates a grid size, and they polish all this tile. This is a polishing line, and so you get into this, you can see. Tile comes in, let's see, here. This is the tile entering the polisher. These are all the polishing heads with the motors. And basically there's a whole bunch of them lined up, and they just polish the tile. And they do it continuously. It's a big business. Polished tile is a big business. Porcelain is the preferred flooring material now. It's become the preferred flooring material. You know why? What's wrong with the video? I have a video. That would be interesting. What do I have the video? It says it's that big. Anyway, why do we prefer porcelain as a flooring material? Number of reasons, right? One, less expensive than natural stone. Two, it's impervious, right? So you don't have a problem of discoloration or absorption of things that are still on the floor. And three, it has superior wear resistance. So natural flooring, you have options like marble, right? Real estate buildings are often have marble floors. You do it on the stairs, what do they look like? And they're all basically cut, depending on the age of the building, right? And then what's great is that that's from people, but it's actually from people that get sand on their shoes or debris, and that's what's degrading that surface. So the Spaniards looked at abrasion resistance of tile. Very, very interesting experiment. And this is a great learning thing. They made this thing. They mimicked the behavior of a shoe in terms of behavior. And so I don't know why I'm taking a picture of that. That makes no sense. So they took a shoe, and what they did was they mimicked the behavior of someone walking, right? And then they introduced a grip. And the grip they introduced was aluminum initially. What they were looking for is the wear or abrasion resistance of these tiles, of tile surfaces in the presence of someone walking on them, so they could look at. There's no standard for this, but what they get is that with alumina, everything fails. That alumina is too hard of an abrasive, and what it does is it just eats through everything. Right? So now they had this device that they built, and then they would say they do 1 million cycles, so it takes a week, everything fails. And they realized that if they put silicon in, quartz, right, then what they get is they can see differences between the tile in terms of their performance. That's the thing. That's the learning point, right? Is that maybe you don't need this to be so abrasive, or maybe you can, when you're doing a test, you don't pick something that the test always fails. But tile performs superior, and porcelain tile performs even better. And you can polish it, and that polishing process improves then the appearance of the tile and other aspects of it. So this is where we left off the other day in terms of spray drying. And so all this material is spray dried. Material comes in basically, and in China, unlike here, if you buy raw materials here, they come in pre-ground. They're ground to a certain size. You're buying that. Okay. The clay comes in. We're talking rail car quantities typically. and then you have your feldspar, naphthalene cyanide, and you have your quartz. Okay. And in here, they don't do that. They bring in the raw materials and they get ground on site. And in that process of grinding, they are also mixing. So they have large continuous ball mills, okay, that take that material in, typically in the slurry form. So there's another benefit of spray drying, and that benefit is that by slurry forming, you get better mixing. So the uniformity of the tile is better microstructurally and compositionally. So that material comes in and gets spray dried, and that provides flow that they need for uniform compaction behavior and dye fill, and that costs a huge amount of energy to do that. And then, this is the spray dryer. So it's quite large. These values are real, and there are larger spray dryers. The thing about spray drying is that nobody, and I don't mean just me, I mean nobody has figured out scale up. You're on a laboratory scale, you go to a larger spray dryer, and then you have to refigure out your conditions. So if we go back a couple slides to here, here. Okay, this one, flowability, right? So you're looking for uniform flow, and you're also looking for uniform flow in terms of size. So they're very interested in those parameters. They do not care about much else. You need uniform flow. So first you got to have the right size. Second, you have to have the right moisture content. Okay. So the size is dictated by atomization and by materials such as viscosity of suspension, etc. Okay. And your flow is dictated by water content. So when they get to here, this what happens is the droplet comes in, goes up, comes around, and it actually, you think it's rotating, but it's not rotating. And what will happen is in that granule, the top is hotter than the bottom. So the granule, right, like this, with T top is greater than T bottom, then you end up with a non-uniform evaporation, if you will. Okay, and so you end up with a thicker top surface, okay, and a thinner bottom. And that thinner bottom will rupture because in doing this, the outside becomes rigid, the inside is still trying to shrink, and so it will rupture. And when it ruptures, it will open up this region, and you end up then with a granule that's like this. And it opens up that void. Once this ruptures, this is now free to shrink, and you end up with a hollow granule. And so that's what this is. But the perception would be that this thing is spinning, okay? And it's not. It's very clear that it's not spinning. It's just a droplet falling through space, basically. It's not spinning, so you end up with a non-uniform temperature gradient, and then or you end up with a uniform temperature gradient from top to bottom. And so what you get here is, if you look at these images, you get that, or you get this. That one looks perfect, but I suspect if we flip it over, it's got a hole in it. So the problem is that when you look at these, you see a percentage of these. You know, in the field of view, we have 1, 2, 3, potentially 4 that have a hole in the middle. But it's very likely that they all do. This one here too has. You can see it's not uniform, but that's the thing that you end up with that non-uniformity. That hole is extremely difficult to get rid of. Do they care? No. They do, but they don't. They live with it. The reason you get the hole is because they drive up the solids concentration in that suspension to be maximized. Why do you maximize the solids concentration? Yes, but it's actually, well, the product is, you could say is you have greater throughput, but the real reason is cost. Because it costs money to evaporate water. The less water you have to evaporate, the less your cost is. And then for the same amount of energy cost, you make more product. So yeah, there's a product thing, but it's really about cost. So we're talking about out number 2, exhaust, powder less than 100 milligrams per cubic meter. The N here is normal, so normal cubic meter. So that's the amount of air that's exhausting through the system, and that air is essentially saturated with moisture. So your incoming air is dry, And it says it's hot air, it is dry, there's no, there should be very, very little moisture in it. It is the waste heat typically from from turbines, not steam turbines that are, maybe it's steam, being used to run power generation, electric power generation. And then you end up with a solids content here of, it's a solids content, but it's about 0.3 to 0.45% moisture. And then your flow rate here, this is the solid content in the suspension, okay, on a weight basis. And then what's coming out, you have 5 to 7% moisture in the granule coming out. And notice that the temperature of the air that exits is 90 to 120 degrees C. The temperature of the granule is 50 to 70. Why? Because evaporation of water is cooling that granule, and the granule never matches. Unless you run out of water. When you run out of water, the temperature of the granule will match the temperature of the spray dryer. As long as you have moisture in the system, the temperature of the granule will be less than the temperature of the spray dryer. Okay? And that tells you the evaporation rate. And what happens is this material stops evaporating. The reason is that there's no room for more water in the exhaust gases. So what they do is they figure this out. This is a unique experiment because this was done in an industrial spray dryer. So they are, let's go back here. They're talking about basically, let's see if we can get one. 10 powder flow rate coming out, 10 to 30 metric tons per hour. Right? So let's say it's 20. You go over here, 20 metric tons an hour. You have four data points at 4 different moisture contents. Okay, so you have 16 times 20. That works out to be 320 metric tons per hour. They're going to take this thing, they're going to set up this spray dryer, and they're going to run it until it reaches steady state. Then they collect the sample. And then they're going to change the parameter, they're going to run it until it reaches steady state, and then collect the sample. And so they're actually doing this test on a spray dryer in a factory. You're creating, hundreds of tons of material, and then the question is, can you use it? Maybe. But by doing this, they then mapped the sensitivity. So you're looking at moisture content on the y-axis, and then this is the slip flow rate. So as you increase the flow rate, you end up with increasing the flow rate means that you're going to basically cool the system. Okay, and so what they have is then your inlet temperature, your outlet temperature now in the spray dryer is a response. It's not a variable. It's a response based on how much moisture is getting evaporated. So you're cooling that air, and then that difference is essentially related to how much suspension you're running through. With this grid, they can then adjust the flow rate. You would assume that this is probably constant. And then what they can do is adjust the flow rate to keep their moisture content uniform. So they set up a feedback loop, okay? And they look at their flux through the system. This is the amount that's coming in. This is their pressure drop across the system. They have their temperature input. And then over here, they're measuring the moisture content. And by looking at the moisture content, the orange here, really poor choice of colors, but that's what I got. So the orange here shows what it was before when they implemented this feedback loop. So by looking at this, they then feedback and they control their flow rate, and they're monitoring the temperature coming in. And now instead of being out here, they're actually operating within this sort of gold yellow color in here in the middle. And you see that their moisture content uniformity is much narrower. This is only 0.8% moisture content to begin with. But by doing so, they substantially improve the fill behavior of that material, and therefore the yields in terms of time. So, cartoon version of what's going on, blah, blah, blah. Then this was our dry press that we had in-house. It was in the 843 lab, which is down the street here. Lennox China donated the press to us. It was a monster, 600 ton vertical linear press. And this was the problem, right? So what you have is we were looking at dry press and vinegar. So you get dry press behavior, and you can see in this is an optical image, And you can see here granules that are still present. So by pressing, we have now what are called semi-isostatic dyes. So semi-isostatic dye for dry pressing is very common now. So what you have is, let's just do it really simple. I'm not going to draw your cross-section of the plate. You have a steel platen, okay? You have your die wall, okay? And then what you have is a die that essentially comes down, looks like this. Behind here is a steel plate, and then this is filled with oil. And so your granulate is here, and when this presses, they bring the press down, then they lock the punch, and then they pressurize with oil, and then this membrane will deform based on the fill variation. So what you get out is a piece, I'm going to exaggerate, it looks like this, right? But it is variable in its cross-section based on fill. That's an exaggeration. I mean, what you would get is very, very small variations that are compensated for in terms of fill by allowing greater deformation of the punch in that region. So it's a semi-isostatic die, but it's a polymer. And so the polymer is unable, it actually deforms around these granules rather than crushing them. And SEM images here. But this is then a surface roughness measurement. You can very clearly see the granules that were not damaged. And so the problem with dinnerware pressing is that in dinnerware press, this is Buffalo, China at the time, they like dinnerware pressing because their production rates would be huge. Their tooling costs are huge, okay, because you have to make that die. But you can produce a huge amount of plates. Your plate cycle time is on the order of like 45 seconds, right? Versus jiggering, where your cycle time is probably closer to about a minute. You may have the numbers, I don't remember what they are, but they're faster than dry press. But the problem is that the way Buffalo China worked is they had a thin glaze. And that thin glaze, the glaze surface was perfect, but because the underlying surface was irregular, and the way that light reflects off the underlying surface, you have the impression that the surface wasn't as good. And so the problem with that was that it was not a very pleasing surface to look at because you could see through the glaze. They looked at jigger. This is you look at this value here, the RMS roughness value is about 8.5 microns. Peak to valley is almost around 90 microns. And your this is an RA roughness. We're interested in the RMS roughness value. And if I go from here, 8.5, if I go to jigger, I'm 3. And that difference is actually perceptible. You can see that difference. And if I go to ram press surface, it's also about 3. So you can see the quality of the surface in the upper right with the surface roughness measurements. Okay, they're really quite uniform. Your peak to valley here is 65 microns. Here, your peak to valley is 80 microns. That's measuring from a very small like divot to the top. So that's not a good measurement. This is a better measurement, 3 versus 8. Okay, so that was the issue with dry press. In tile compaction, they also do a semi-isostatic die, but the pressed surface against the steel, so the bottom surface here, is against steel. So the granules get deformed. You get a perfect surface, more or less. And the back then can have the variation, can have the roughness, and they actually prefer to have the roughness on the back of the tile because the roughness then contributes to the bonding of the tile to cement and the installation of the tile. So they like that roughness in the back, so they don't mind casting over. Plus, they flip the tile over, comes out, and typically it's pressed so that the smooth faces down. And then when it's done pressing, it slides out onto the rollers and goes directly into a roller kiln, right? But usually what happens is sometime in there, it comes out, and then if they're going to do a print, they'll do the print online, but they'll take that tile and they invert it. In that. They don't. It's very interesting the way they do it. It comes into a huge rotating thing, and it's basically held in place and it gets inverted. So you're not actually ever flexing the tile. But then you have the top surface up going into the furnace, and then they can print their design on that top surface and it goes into the furnace and then gets fired. I'm going to talk just for a second about firing tile. Because I have a problem with it that I can't figure out yet. let's say I have a tile that is, let's say it's like this, okay? 3 meters by 2 meters, and it's going through a roller hearth kiln, okay? So if you think about the way a roller hearth kiln works, it's essentially like this. It's a long kiln, okay? And there are a series of rollers, basically, and they're all turning. And so the piece of tile comes in, looks like this, goes to the roller hearth kiln. The temperature profile looks something like this, comes up, comes down like that, okay? Time frame is 50 minutes from cold, which is room temperature, to ideally cold on the way out, which would be room temperature. Of course, it isn't. Tile's still hot when it comes out, okay? However, the problem is this. In that firing process, if I orient it this way, or if I orient it this way, right, doesn't make a difference. Moving through the kiln, okay, this surface, the front leading edge, will be hot before the back leading edge is, and in fact, it will sinter first. So you can look in the kiln and you can see that it's something like this, right, and it's actually sintering as it goes through, and it is shrinking non-uniformly as it goes through that. It comes out fine. Now, this, in my opinion, is a game changer. You see it in other cases too, that this idea of continuous sintering and the stresses involved for shrinkage. This further argues that all of our problems associated with cracking and shrinkage, and cracking due to shrinkage during firing, have only to do with processing and nothing to do with firing. In my opinion, we have to change we need to reevaluate everything we know about sintering in the context of this and defect generation during firing, because they can do this. We have an really interesting problem that we think is true. This 50-minute thing is the other. So we're trying to figure out how to measure it. We think we can do it. If I take this tile, okay, and I have, say, let's say 2 centimeters, and I'm cooling that tile that quickly, so my peak temperature here is typically around 1200 to 1250 degrees C is my peak. Okay, it's at the peak temperature in a 50-minute cycle. It's at temperature for 6 minutes. At peak temperature for about 6 minutes, which, by the way, is 0.1 ounce. Okay, and we demonstrated fast firing, which we're going to talk about on Monday. Demonstrated fast firing that that time frame. Fast firing is not a unique situation, that it is behaving in a continuous manner based on a log time scale. So 0.1 hours versus 1 hour versus 10 hours are continuous. The problem is that the surface of this tile and its thermal expansion coefficient will cool much more rapidly than the interior. Okay, you've all had introduction to glass, right? Talk about tempered glass. You know what tempered glass is? So what they do is they rapidly cool the surface of the glass to let the surface of the glass solidify while the inside is, we call it the jelly center, right? That's what I call it. And so then that interior surface, that interior volume is contracting, and by doing so, you end up with a glass piece, and you end up with stress profile looks like this, right? So you have compression on this side, tension on this side, and you have a depth, right, associated with that tension or compression. And so you have this surface compressive layer, so you have tempered glass. And the tempered glass idea is when you have tempered glass, if you get a nick that goes sufficiently deep into this region, and that nick gets into the tensile region, right, then the piece shatters, right? And what's great about that is this turns out to be a remarkably efficient, life-saving device, particularly in automobiles, because then the glass, and it's required by law now on all doors and windows that are, where people walk or whatever people are at, because then you break up a little bit of pieces of glass. You think that because of the rapid cooling that occurs in firing in tile, that we have the same situation in tile, which is really fascinating. And you say, well, what's the deal? The deal is that you have the thermal expansion coefficient for the tile, okay, which we're gonna talk about later, but you have a finite thermal expansion coefficient, and you're cooling that system extremely quickly, okay? And when you cool that system quickly, you place the surface in compression. And the evidence for this is when they take these large format tiles and they start cutting them, they will often randomly crack. Now, you're cutting, there's no stress in the system other than cutting, and a crack will shoot on its own. You don't get the shattering that we get, okay, in glass, but we think you have a surface compressive layer, and as you cut, the water jet cutting, so you're in a pretty benign situation to begin with. So water jet is high pressure water with abrasive, and they'll cut, say, a sink opening in a large format tile, and then that crack will propagate. And so we think that this is a problem of that cooling is too rapid. When cooling is rapid, you end up with stresses. Now, in tempered glass, how do I detect the stresses in glass? You know that you can do that, right? Typically, we do it optically. The easiest way is optically. You take cross poles, right? You take polarized sheets, and you cross them. And so when light comes through, it gets plane polarized one direction, and then it's 90 degrees to the plane polarization of the next, and you get opacity. And when you put in a poorly tempered piece, it bends alike. You can then see it, right? So if you take tempered glass, you can see the stresses that are still in the glass. You can't do that with porcelain because it's not transparent. So how do I do it? We think we can do it by fractography. We can look at the fracture surfaces and determine there's a surface compressive. So I think that you will be pleased for me to stop here today. Is that good? So what we're going to do on Monday is drying. Then we're going to get into firing. Okay. And I think on homework standpoint, this should. Oh, there is one more thing I forgot to do, and that is this compatibility, polymer compatibility. So give me just a second to do that, and then. That will wrap it up for us. We've done a lot of work on polymer compatibility in the past several years. We sort of abandoned it of late. Yeah. So we have an interesting phenomena in spray dried materials. We do not see it in tile, but we see it in dinnerware. It has to do with PVA. Polyvinyl alcohol is the most common binder used on the planet, and that's just unfortunate. There's nothing we can do about it. And the reason is that some researcher in the 1950s put PVA in with bearing type, found that the strengths improved. So then it became the binder of choice. PVA is typically used for sizing on cloth, on fiber for making cloth. So what it does is you have cloth, of course, like if you make cotton fiber, it's a whole lot of fibers in the cotton plant that are more or less tangled together to make a thread. And then you have individual strands of that that stick out. It's essentially a cellulosic fiber. And so what happens is that those little strands, they tend to break off. And then you build up this mountain of these little strands and start making new fiber in the loom, and then it creates all sorts of problems. So what they do is they essentially coat that with a polymer to keep those all intact, so the fiber stays intact, and then they can weave cloth much quicker and with less problems. So what we have on the left is polyvinyl acetate, and then we have on the right is polyvinyl alcohol. And in the presence of sodium hydroxide and high pH and methanol, you eliminate these acetate groups in the formation of the hydrate. Okay? But you have these sticking off the edge. Okay? So we have a degree of hydrolysis, which is the ratio of these two. Now, we don't care about much of this at the moment, but I'm not going to do this either. This is something that's ongoing. what we found is that when you put PVA in water, this is a good illustration. This is PMAA, so our dispersant with PVA, and it will phase separate. This is polyacrylic acid with PVA, and it phase separates. But when you sodium silicate, it actually is much better. Okay, and then this is lignosulfonate, which is a byproduct of paper making. It looks nasty, but actually it's a pretty good binder. It's very commonly used in structural ceramics, clay, and clay pipe for like sewer systems and that sort of thing, which is not very common. Okay. And you look at turbidity, you find that there's an optimal mixture where the system becomes turbid. Okay. And it has to do with the ratio of PVA to PMA. So we did this compatibility thing. I'm just going to go to the punchline here. Okay, and we did this. We made spray dried granules. And then we took those spray dried granules and basically froze them, fractured them, and then we treat this surface with a boric oxide solution. So it turns out that boric oxide really likes PVA. It doesn't care for our particles. So the boric oxide goes to only where PVA is. Then what we can do is we can bring in iodine, which gives you blue, black kind of concentration, and iodine only goes where boric acid is, right? So if you've ever made, ever do the STEM thing, you know, the fun and games with kids, and you make slime, you take PVA plus boric oxide, right, or borax, and boric oxide and boric acid will cross into PVA and you get slime. That's the idea. But here, this goes to where the PVA is. And so what you see is that, and then we go back with the iodine, we then decorate boric oxide. So this is a fracture surface. This is the better image here. PMAA, and you can see that the PVA is only more or less on the outside of the granules. But that's really true with PA, polyacrylic acid, PAA. You have no PVA in the middle of the granules. So what you get is a phase separation phenomena, and you get case hardened granule if you use PVA in the presence of the dispersant. Now, if you do sodium silicate, it turns out there's very little migration of PVA, much more uniform distribution of PVA. This is better. It's because PVA likes silica. PVA does not like aluminum. So, and it doesn't like polyacrylic acid. So this phase separation then creates a case hardened granule. And a case hardened granule flows great, okay? But a little bit of humidity or PVAs along the surface, they tend to stick, so you have a problem that way. The other thing is that they will not break down uniformly to pressing. And you can see pressing direction is perhaps obviously this way, it's horizontal here, and it squishes these, but they're not really breaking down the way you might expect. The granule integrity is still evident in microstructures. So PVA turns out to not be compatible with polyacrylic acid, something we should consider moving forward. Have a nice weekend. Thank you for coming to class today.